G times mu sub b plus s plus y 3kb times b plus t in this problem. Now we have, instead of b, we have a b of mean field plus b. So b should be replaced with that. One reminder. Note that you have extra 1. This is because the spins are quantum mechanical objects. And note you have a 3 because magnetic moments are in 3-dimensional space. They can point, they have x component. If you treat the s to be a vector, or even as the operator, it has 3 components, x and y and z, right? But the magnetization, we're talking about the component only in one special direction, in the direction of the magnetic field, right? So you have a the object which has a 3 degrees of freedom, and you make a projection into the one direction. That's why you have a factor of 3 here. So the spins it has 3-dimensional object. It has x and y and z, whereas magnetization spins. Okay? Whereas magnetization, you're talking about something in one special direction, right? That's why I have a factor of 3. Okay. Now, what was B sub mf? It was defined there. I'm looking at only the component in the direction of the magnetic field, so all the vector signs have disappeared. Z times J times M divided by N Avogadro divided by G mu B squared. Okay? So we have this situation, magnetization with respect to the maximum magnetization is approximately G times mu B S plus 1 divided by 3kb times Z times J times M divided by N Avogadro G times mu B squared plus B. Okay? So you have magnetization M showing up on both sides. So you can solve this by moving this term to the right-hand side. I'm sorry, the left-hand side. Then you have a 1 minus. There's a cancellation. So 3kb Na G times mu B. No, what am I doing? Okay, move these guys here. So Z times J S plus 1 3kb Na G times mu B once, and then I have ms, so multiply with ms is approximately the remainder, so G times mu B times S plus 1 times the magnetic field divided by 3kb. Hey, what's happened to my temperature? Something is missing. Okay, T. All right, I have forgotten that T. So 3kb T. Okay? Then T should be here as well. Yep. Okay? Now what's the maximum magnetization M saturation? That's N Avogadro times G times mu sub B times spin quantum number S, right? So this Na times G times mu sub B will cancel out with this guy. So let me rewrite this part. It's Z times J times S plus 1 times 3kBT. Okay? Did I do it right?
Excuse me.
Yes?
What is QM?
Oh, quantum mechanics. I said this is the effect of quantum mechanics. Okay? The fact that the spin is a quantum mechanical object, that's why you get this crazy one in addition to S, which is the same as when S is very, very large, S approaches the limit of infinity, then the difference between S and S plus 1 is negligible, right? So that suggests you this is a quantum mechanical effect. Okay. All right. And this combination is defined to be theta, Weiss temperature. It's a Weiss temperature. Okay. So what we have found here is this. Magnetization in the unit of the maximum magnetization, 1 minus theta over T, is approximately G times mu sub B times S plus 1 times B over 3 kBT. Okay. Solve this for that, then you get this result which you're familiar, 3 kb times T minus theta, G times mu B, plus S plus 1 times B. Okay? Compare this with the S. Yes, great, where theta, something is wrong. That's okay. Looks okay, where theta is defined that way. The number of nearest neighbors, the interaction between magnetic dipole moments times S plus 1 divided by 3 kb. All right? This makes sense, right? Because J is the dimension of energy. This is a spin quantum number. So energy divided by kb has the dimension of temperature, right? So theta can be right next to the actual temperature. Now let's take a look at the magnetic susceptibility. The magnetic susceptibility in the limit of magnetic field going to 0, so zero field magnetic susceptibility, is the, I'm talking about molar magnetization. In other words, the total magnetic dipole moment of 1 mole of ions divided by the H field, right? And the H field is related to the B field in SI unit in this fashion. Okay, but this magnetization is per volume. Okay. But similar to this, we use the molar magnetization per mole. So the definition of molar susceptibility is analogous to the magnetic susceptibility defined in electricity and magnetism in undergraduate physics.